Hello and welcome back to another episode of Math with Son. Today we're starting a new unit on AP Physics 1, work and power. So work is a relatively easy thing to understand. It is, the physics definition is the x direction, the x distance, this horizontal distance. Sometimes you can think of it as the vertical distance, but most of the time you're thinking of the x distance. And if it is in the exact same direction, it is just your force times your displacement, okay? So, and if it's not in the exact same direction, let's say that you had an angle, let's say you had this upward force right here, you would have to take it into its component forms, and you would only be concerned about the amount of force that's in the x direction, which means if it's not in the exact same direction, you would have to use your work is equal to your force times your distance times cosine of theta, which would allow you to get that x component of the direction, okay? So that's work in a nutshell. You only got those two formulas. It's not that complicated. Sometimes you intertwine other things, Newton's laws, friction, as well as even kinematic equations. So with that in mind, the unit for work is an important one for you to know about, is called joules. The unit for work is called joules, all right? And another thing you'll hear sometimes, this is a very intricate topic, it's like a whole different video later on, is conservative force versus non-conservative force. And for right now, I want you to think of conservative forces where energy is kind of conserved, and versus non-conservative force would be when it's not conserved. So non-conservative force would be something that involves friction and things like that. All right? Unit for work, joules. All right, let's do a few examples and we'll be done with this video. So this first example is really just determining if work is done in any of the cases. And what I want you to think about with work being done, I want you to think of your mom or your dad telling you to clean your room. Clean your room, okay? Now, if you go and you clean your room and they come back and it looks completely spotless, it's clean, they're gonna say, wow, good job, you did some good work here, son or daughter. But if they come back and you did clean your room, but then you immediately went and made it messy again, from your parents' perspective, you didn't do anything. So work is only accomplished when you can see that change, all right? So here, where we have a weightlifter holding 300 weights above his head, from an outsider's perspective, if they left and came back, they would be like, well, you haven't done anything, dude. Even though he's sweating holding this weight, there's no work being done at all. Okay, no work done. And another way to think of it is that, let's say you had this table right here, and on this table there's a plate of food. Would you say that table's doing any work on the plate? No, it's just sitting there. It's not accomplishing anything. It's not moving. There's no work being done. All right? What about a hockey puck that is moving at a constant speed on a frictionless ice surface? Well, here the key word is constant speed. And if you remember correctly, for force is equal to mass times acceleration, if it's a constant speed, there is no acceleration. That would be 0 meters per second squared, which means that even if it has a mass of like half a kilogram times 0 means there is no force. If there is no force, there can be no work, because remember, work is equal to force times that displacement for x. So 0 for force would mean 0 for x, would be 0 for your work, because 0 times any displacement would be 0. So also no work. And then the last one, we have a crate being pushed across the ground at a constant speed. Now this is kind of tricky, all right? It is being pushed. That initial push is a force, but the constant speed is not. Okay, so if it said constant acceleration, there would be work being done here. But if it says constant speed, the only real work that would have been done was that initial jolt. And then after that, it would be just kind of moving at a constant speed. But typically, if you have a jolt and whatnot, you're going to have a constant acceleration. So this would need to be acceleration for there to be work. But because there is no acceleration, it was speed. It again is no work being done. A lot of times, just like me, teachers tend to show you what is not considered work, because it's a lot easier to make a mistake in thinking, oh, that's work being done, when it's not. All right? Few other key pointers. Work is positive if it is, work is positive if the component acts in the same direction as the displacement, meaning the work is happening in the same direction as it's being, the force is happening in the same direction. Versus if it's going opposite of the direction, for instance, friction would act in the opposite direction of the force being applied, or specifically the displacement being applied as well. So friction opposes you, therefore it would be acting in the negative direction. It would be acting against you and would be conducting negative work against you. Work is zero, no work is done if there is perpendicular force to it, to the displacement. All right. So we'll do a few quick examples and then maybe call it a video. We'll see. I might do all the examples in this one. So a skier is skiing down this slope. Nice. Draw a free body diagram of the skier's motion and identify the force that does positive work, the force that does negative work, and the force that does no work. So here we have this skier. And this skier is going to be having its, sorry, get the right page here. All right, the skier, I was debating whether I wanted to draw another picture. I think I will. The skier itself, he is going to have the force normal on him. It would have, albeit a little bit, not a lot of it, the force of friction acting against him, and we would have the force of gravity hurtling him down that slope. Okay, so we've drawn the free body diagram. The only part of the gravity that will be affecting his downward momentum will be this part right here, that in the same direction as the displacement, and the displacement is technically the x value, which is why for work, for cosine, we use FD cosine theta typically, although this one's different because he's on the incline and you actually would have to probably end up using, nope, the incline's here, FD cosine theta, excuse me, sorry. All right, so with that in mind, that's part A. What work does positive work? The gravity would be doing the positive work, but only in the same direction as his motion. The force of friction would be doing negative work. This would be the positive work. And the force that does no work would be the normal force. All right? And I think I'm going to call it for that one. I want to keep doing some separate examples in another video because the separate examples take a little bit more time. This is just the introduction to it. I will see y'all in the next one. Bye, folks.